All right. Well, a couple things. It is Tuesday. We're going to start a new lesson today, the binomial theorem, which is all about expansion of binomials. Okay. We'll talk about a couple different strategies to do that. Right after we get to our focus activity, this is the last one for our current set. Now, they are due tomorrow. That's the last grade of the 6 weeks. If you want to turn them in today at the end of class, that is perfectly fine. We just will wait until we're done with the lesson for today. I did get a chance to look over the district assessments. I got a copy of those yesterday. We are ready to go. So I've ultimately decided that we will not be taking the last part of class tomorrow. In order to begin them, we should be able to finish them in just one class period. And you're probably asking, well, why? Looking over the district assessment, this is another one of those tests where the majority of the problems are on material we have not yet talked about. In fact, there's only 7 questions on this district assessment that you actually should be able to answer. The majority of them are over conics, parabolas, ellipses, hyperbolas, and that's exactly what we're starting next week. So I cannot get out of giving the district assessment. I've been told I have to give it, so we just have to take that day. So I'm thinking for those 13 questions, I'm just going to encourage you, make your best guess. Does anybody know anything about conics? Parametric equations? Nope. Then I'll encourage you, just make your best guess, maybe abacadabra all the way down, but at least try to answer the questions that are familiar to you. Okay, whatever it is you want to do. So that's coming up. You know, we're going to have an unusual schedule next week. Tuesday and Thursday are the English star days. So that's all I've got for the near future. Does anybody have any questions about what's coming up? Yes.
Do we just come late?
Yeah, there'll be late start days. I want to say, are you reporting 1:15 or 1:30? I can't remember. I don't know. I'll double check on that. They have not sent out a schedule of who's administering and who's going to be break givers and basically all the jobs involved with giving a STAR exam. More than likely, I'm going to believe I would be giving the STAR exam. So as soon as I get that information, I will pass it along to you guys. But yeah, if you are not taking one of the exams, you will not show up until the afternoon. We'll have an abbreviated schedule. Yes, sir. Tuesday and Thursday of next week, the 9th and the 11th. Okay. All right. The only other thing I want to mention, we have less than 2 days if it applies to anybody. Oh, and Susie, I'll get to you in just a second. Thursday morning by 8:05, if there is anything outstanding, retake you want to take care of, maybe from last week's exam, if you have an outstanding homework assignment, anything of that nature needs to be taken care of by 8:05 a.m. on Thursday, because right after that, I'm going to start finalizing the grades. Yes, ma'am. Now, I would imagine, this is just a guess based on what I've seen in the past, because like I said, they haven't released that information yet. So I would think on Tuesday, we'll more than likely be going to periods 1 through 4 in the afternoon, and I would think Thursday would be periods 5 through 8. Okay, but then you never know. They might decide to switch them because reasons. I don't know. But as soon as I get that information, I will go ahead and let you guys know. And there's still plenty of time in the week, so hopefully they should be sending that pretty quick. Okay, anything else? Okay, well, let's get to our focus activity here, because these look like really good problems. Has anybody already finished up the entire focus activity? Few folks, good, good, good. All right, well, let's see. Number 1, Valeria joins a social networking website. After 1 week, she has 34 online friends. At the end of 2 weeks, she has 41 friends. After 3 weeks, she has 48 friends. And after 4 weeks, she has 55 friends. Okay, so whatever she's posting, people are liking. There you go. So A, show that Valeria's number of friends forms an arithmetic sequence. Now, the number of weeks, that's the number of terms that we're looking at. So week 1 is term 1, and the value is actually 34. So let me go ahead and generate this sequence. So 34, second week is 41, the third week, the third term, 48, then 55, and that pattern hopefully is going to continue if it's going to be a sequence. Well, what can I easily do to show that this is arithmetic? Okay, Scott? Just write arithmetic? There you go. Okay, so 7 is what we're looking for. So remember, if we're dealing with an arithmetic sequence, I should be able to subtract consecutive terms and get that constant difference over and over again. So it'd be enough to show 55 minus 48 is 7. The 48 minus 41 is equal to 7. 41 minus 34 is 7. So I know I can go ahead and confidently say this should be an arithmetic sequence. In fact, what would the 5th week be? 62 friends, and then we can just keep going on that. Okay, good. So B, assuming the pattern continues, find the number of online friends Valeria will have after 12 weeks. Now, it doesn't ask for it specifically, but I would recommend finding the explicit formula and then plugging into that in order to find the answer, because that equation can actually help us with part C. So here's the explicit form of an arithmetic sequence. Remember, the nth term was the first plus n minus 1 times the common difference. Well, if I wanted to know the formula, I plugged in every value except what? Excuse me. N. I left n alone. So we know the first term is, what do we got here? 34. So a sub n is equal to 34 plus n minus 1, and we said the common difference was 7. Okay. So instead of writing it out again, I'm just going to go ahead and simplify this. 7 times n minus 1, well, that would be 7n minus 7, right? So what's my explicit formula? What would the nth term equal? 7n plus 27. There we go. That will get me any term or week number that I'm looking for here. So we want the 12th week, so I just plug that in. So a sub 12 would equal 7n, 7 times 12, plus the 27. Excuse me. So let's see here. Jasmine, how many friends would she have after the 12th week if this continues? $111. There we go. 111 friends, just like that. Okay. And now C. After how many weeks will Valeria have 150 online friends? Well, how would I do this? Yeah. So what we're going to do is plug 150 in for A sub n. We're looking for the number of weeks. So basically, what term number is she going to hit 150? So let me come down here where I have a little more room. I'm going to take the 7n plus 27. I'm going to set it equal to the 150. So subtract 27, I have 123 is equal to 7n. Now, if I go ahead and divide through, what do I get for n? You are going to get a decimal. In fact, it's 17.6. Now, when we're talking about our term numbers, remember, we can't have a portion of a term. We have 17th term or we have an 18th term. So which would be more reasonable if I were to say 17 or 18? I'd say 18, because if your only two choices are 17 and 18, well, it takes until 17.6 until we get that 150. So if I did say 17, we'd actually be less than the 150 we're looking at, right? So with the rounding, I would say that 18 weeks is more reasonable. Anybody having problems? Okay. All right, let's talk about some rabbits. The initial population of rabbits on a farm was 50. The population increased by 7% each week. Okay, what I did here, I really didn't go from a geometric sequence point of view. I went more from an exponential. In fact, I've shown you this before. The amount is equal to the initial times 1 plus or minus your percentage to the power of years. Okay, or in this case, we're talking weeks. Okay, to the power of time. You guys remember that? So what would I be doing here? Would I be adding or subtracting the percentage? Adding, okay, because we're increasing the population. So let's see, the amount should equal, we started with 50 rabbits. What would be the base, the common ratio here? 1.07, because 1 would represent the initial 100% population, the 50. So we're going to add 7%, 1.07. Okay. So what do I need to do in order to answer A1 and A2? Just plug in, like t equals 15. And in fact, I might already have that. Oh, do not. So 50, parentheses 1.07 to the power of 15. So when I push enter, okay, whoop, I'm going to get 137.9. Okay. So again, what would you think? Jackie, okay?
No, there's only part of a rabbit left.
Well, I mean, maybe the rabbit was left alive, but its paw was removed. Lucky for the person, not so lucky for the rabbit. I personally wouldn't care at all for that. I wouldn't care at all. Come on, now that's clever. Oh, you just thought I was being mean to rabbits. You should have heard first period's conversation. Some people were talking about these rabbits are going to develop some kind of mutations. I was like, good God. Okay. Anyways, so what would you like me to put as an answer? 100 what? So you say 137? Okay, now explain to me your reasoning. Even though it says 0.9, why would you not say 138? Because what?
Yeah, it's not fully.
Okay. All right, so you would go ahead and go with just the whole number of rabbits that we have? Okay, I can agree with that. 137. Would there be any argument to say 138? There wouldn't?
There would be, but they would be wrong.
There would be, but you would be wrong. Why? Wouldn't you consider that portion of a rabbit, especially with such a high decimal, to be just another rabbit, even though we realize there can't be a portion of a rabbit? Well, I mean, there can be, but, we're not talking about a highway or something.
To complete that final portion, that 0.1, you need to add more time, which you see is your 15-week time limit.
Yeah.
Which means you'll have more.
Okay. All right. So that's interesting, because the other two classes said 138. Okay, there you go. All right. So 137. In fact, somebody help me out. What are we getting for A2 if I plug in 30? 380. Okay. All right. And see, as long as you have, some kind of justification for your answer, you're saying, like in this case, I believe I got 380 like 0.6. So you're saying we cannot have a portion of a rabbit, so we're going to go with the whole number of rabbits that we have. Okay. As long as you have a justification, see, that is what's good. What about B? How long would it take for the population to reach 500? Okay, there we go. So what do we do? Okay, so we got my equation here. So this time we're working backwards. We're trying to find the amount of time to get 500. Okay, so we go ahead and divide through by 50. That would give me 10 is equal to 1.07 to the t. You could solve it as a logarithm. You could graph each of these in a calculator, go ahead and find the intersection. I mean, there's a variety of ways. I personally went ahead and used a log. Does anybody remember, if you could describe a log in one word, what is that? What? Well, it is an inverse of an exponential, that's true, but a log is a power, specifically the power placed on the base to get what we call the argument. So if I were to rewrite this, log base 10.07 of 10 should equal the time. See, whatever log expression you write, it has to equal your power, the exponent. So in fact here, I think, what did I end up getting? I can't remember the decimal. It looks like I didn't write it down, but I did put 34 weeks as my answer. And if you go ahead and plug that in, you'll notice I want to say to the 34th power will get you like 498 rabbits. But then if you go ahead and plug in 35, it jumps you to 533. Okay, so 34 is the much more acceptable answer. Okay, any questions? Okay. Okay, we're done with the focus activity? All right, I guess we better hop to it. Rabbits. Okay. All right, let me go ahead and erase this. Now, don't worry about turning in those folks' activities right now. You'll have a few minutes at the end of class. Okay, well, they are officially due tomorrow. Now, how many people are familiar with the binomial theorem? Okay, some of you are. Great. I'm going to be showing you two different strategies. For a while, we're going to go ahead and go back and forth. Some problems we might look at one, which is Pascal's triangle. The other one is using a combination. Maybe, maybe not. That's going to be familiar. We'll see. But let's get right to it. The operation of multiplying a binomial to a specific power, then writing the polynomial in standard form, is known as expanding. So one way that we can easily do this is by Pascal's triangle. A rectangular array of numbers in which the first and last number is 1. Each of the other numbers in the row is the sum of the two numbers above it. Okay? So here's the thing. One thing I want to go ahead and point out first, before we go ahead and talk about how these rows are generated, is when you start counting from the top, you start counting with 0. Very, very important that you always start counting with 0. So the very top isn't the first row. Okay? Then this right here, 1, 1, that's the first row. Then we have the second, third, fourth, and we count from there. Now, in just a few moments, I'll go ahead and make the connection why we start counting with 0. Okay? But the first items here, the first rows, we have 1, 1, 1. You always start out Pascal's triangle the same way. So it's probably going to take a couple of rows for you to get the idea, but you bring the first one down, and then the consecutive numbers, you add those. See, 1 plus 2 gives me 3. 2 plus 1 gives me 3. And then we bring the last one down. The thing about these rows, they're going to be symmetrical. Okay, so now let's go from 1, 3, 3, 1 to the next row. So I bring down the 1. 1 plus 3, 3 plus 3, 3 plus 1, and then bring down the 1. Okay? The next row is always generated by taking the sum of the previous numbers directly above it. Okay, so if I'm going to use 1, 4, 6, 4, 1 to generate the next one, bring down the 1, 1 plus 4, 4 plus 6, 6 plus 4, 4 plus 1, and then bring down the 1. Okay, so let's go ahead and generate the next row. In fact, how many rows am I showing here? 8. So this last one right here is the 8th row. Well, why don't we go ahead and create the 9th row? So I'm going to bring down this 1, and then 1 plus 8. 8 plus 28. 36. 28 plus 56. 80 what? 84. Now 56 plus 70. 126. 70 plus 56. 126. And what are you going to notice it does from here on out? Yeah, it's going to repeat these same values. So again, 56 and 28 will give me the 84. Then you'll get to 36, to 9, and then to 1. So that would be row 9. And then we could easily go ahead and generate the next row by continually taking the sum of the two numbers above the number we want. Is everybody okay with how this is generated? Any questions? Okay. Well, how is this going to be useful to us? Well, I'm glad you asked. Okay. Come back over here. Let me cover this up real fast because we're not ready for it. Let's do it the old-fashioned way, what you were taught way back in a good old Algebra 1. Let's say I want to take a plus b cubed. Well, what is this actually telling me to do? There you go. The power tells me how many times I want to take that base and multiply against itself, right? So let's take a plus b times, and I'm going to go ahead and put the second 2 in brackets because I'm going to multiply those first. A plus b, and there we go. And squaring, cubing, we've done those for a very long time. In fact, what's the acronym we like to use to multiply these? FOIL, first, outside, inside, last. So the first a plus b is going to remain the same. Okay, let's go ahead and multiply a plus b times a plus b. In fact, what's the trinomial I would get? A squared plus 2ab plus b squared. Okay. Now, how am I going to multiply a binomial times a trinomial? This goes way back to the good old days. There you go. It's just the distributive property. I'm going to take A and multiply across the trinomial, and then I'm going to do the same thing for B. So you guys help me out. A times A squared. A cubed. A times 2AB. 2A squared B. And A times B squared. AB squared. See, I've taken care of the A. Well, now I'm going to distribute the B. All right. So what's the fourth term? Or at least what I have right now. A squared B plus 2AB squared. And finally, we finish up B cubed. Now all that's left is to go ahead and combine your like terms. Remember, it has to have the same variable set and power set. So A cubed is unique. There's no other cube to add that with. This is A. Plus, I need a 2A squared B plus A squared B. 3A squared B, right? So now I need an AB squared plus 2AB squared. 3AB squared. And then we finish up with plus B cubed. Okay. Well, the question was, why are we looking at Pascal's triangle? Why is this useful to me? What was the power I wanted to raise this binomial to? 3. So why don't I come back up here and look at the third row? What are the numbers that I have here? 1, 3, 3, 1. What do you notice? That's exactly the coefficients that I ended up with when I expanded the binomial. Okay. Now, if your coefficients of your binomial are just 1, like here we have 1a and 1b, the numbers from Pascal's triangle will be your coefficients. But if you have something like 2a plus 3b, different coefficients, you're going to have to multiply those by the numbers you find in Pascal's triangle. Okay. Basically, we're going to be able to use patterns that we notice, okay, so we won't have to do this kind of work. We can immediately generate the answer. That's what the binomial theorem is going to be able to do for us. Okay. Now, I kind of skipped over it. There's the definition right there. I'm not really worried about reading it because a lot of times, definitions in mathematics can be as clear as mud. But if you have any questions, just let me know. Now, let's try the other one. Let me give you about a minute or two. I want you to do the exact same thing. But this one is A minus B cubed. Okay. I want you to expand that the old-fashioned way, just like we did the previous one. But there's something you're going to notice, something I want you to pick up on. Okay, so it looks like a lot of people are getting right there near the end. Okay, you're probably really close. So for those folks who have finished, do you notice anything? Okay, what are we noticing? Okay, The terms themselves are identical. A cubed, 3a squared b, 3ab squared, b cubed, but it's the what that changes. It's the signs, and they alternate. So you'll notice the first term is still going to be positive, but now it goes positive, negative, positive, negative. Now that pattern would continue for however many terms I have. Okay, so whether it's a sum or a difference, raising it to a power, if you recognize the patterns, again, that goes a long way in helping you get the answer quicker, and you don't have to do a lot of work. Okay, so let's connect it back to Pascal's triangle again. Okay, so the question was, why do we start counting at 0 for the very top of the triangle and then go 1, 2, 3 all the way down? Well, in order to answer that, let's kind of recreate the first part of the triangle. So I start with 1, and then I go 1, 1. And then the second row is 1, 2, 1. What was the third row? So 1, 3, 3, 1. And you'll notice I'm leaving space here because I'm about to introduce you to a combination pattern. And then for the next one, I would go ahead and say 1, 4. What would it be? 6, 4, and 1, right? Okay. Well, the reason we start counting at 0 and why we have 1 at the very top is because if I take 0 and place it as a power on anything, I'm always going to get what? Okay, 1. But if I raise a binomial to 1 power, you get 2 terms. If I take a binomial to the second power, I get 3 terms. In fact, down here at the bottom, I've got some patterns that I'm hoping you'll pick up on, but I've already gotten them written. Well, let's go ahead and write this out. Whenever you go ahead and start to write the combination of your terms, now we're always going to refer to the first term as A, the first term as B. A will always begin with the power in the original problem. Like, for example, if I want to raise it to the first power, it's going to be A to the first. B is going to start at 0. Now, what you're going to notice is the A terms powers will descend. They're going to reduce in decreasing order. The B term powers, those are going to ascend. So the A powers are going to count down, the B powers are going to count up. So for this second term right here, I would have A to the 0, B to the first. Because ultimately, wouldn't that just give me A plus B? Anything to the 0 power is 1, remember? Okay, so now let's do it here. And it's probably going to take a few rows for you to actually start to really see what's happening. So here, I want to square it, right? So the very first combination, I'm going to go ahead and say A squared B to the 0 plus. Then I move on to the next term. The A powers will count down, the B powers will count up. So the next one would be 2, oh, I don't know why I put the 2 again, AB. Plus, by the time we get to the third term, A to the 0, B squared. But in order to start the combination, the A term will always begin with the original power on your binomial. Okay. Can anybody start me out here if I have A plus B cubed? There you go. So that would just be A cubed, B to the 0. Now, right here, I'm really just trying to emphasize the pattern, which is why I'm putting the 0 powers in here. Once you become comfortable with this, you don't have to write those out. Okay. I mean, even if you do, fantastic. So what would the combination be after A cubed B 0? It would be A squared B to the first. Then it would be A B squared. Then finally A to the 0 B cubed. Is everybody starting to see the pattern? The powers on the first term A will descend or count down. The powers on the second term B excuse me, will ascend or count up. So here I want to raise A plus B to the fourth. So what would this first combination be here? A to the fourth, B to the 0, plus, for what? A cubed B plus A squared B squared plus A B cubed plus A to the 0 B to the fourth. Okay. So this first one that I've got written here, in order to notice it, I pretty much had to show you for every one of these rows, right? Okay. So is everybody okay with the fact that the A powers will descend, the B powers ascend? Any questions on that? Now, a second item I've got here, it says the sum is always the original power. What does that mean? Like the number of A's and the number of B's? Like you're talking about as a cumulative sum?
No, just like
Okay, so like for one term. Okay, like here, I'm raising A plus B to the fourth power, right? So look at each individual term. If I add the powers on one term, what's 4 plus 0? 4. Here we have 3 and 1. 3 plus 1 will give me 4. Here we have 2 and 2. That's what we're referring to. The sum of the two different powers should always give you the original power you started with. Okay. Well, what does it mean always one more term than the original power? So always one more term than the original power. What's that referring to? Okay. Satish?
I guess for like the fourth example, or like the A plus B to the fourth, you'd have 5 total terms.
There we go. We're talking about the total number of terms in your answer. So if I'm going to raise it to the fourth power, we'll look at how many terms I have. 1, 2, 3, 4, 5. That's what it's referring to. The number of terms in your answer should always be one more than the power you started with. See, if I'm going to cube it, then I should have 1, 2, 3, 4 terms. If I'm going to square it, 1, 2, 3 terms. Okay. So if I wanted to raise something, a binomial, to the 20th power, how many terms in my final answer? Should be 21. It'd be a very long expression. Okay. So let's try an example. Okay. Let's take A plus B and let's raise it to the 8th power. So this is definitely an example. We don't want to sit here and say A plus B times A plus B times A plus B 8 times. That's going to take a lot of time. It's very likely you'll probably make a mistake at some point. So let's use Pascal's triangle. Because I'm raising it to the 8th power, well, how many terms should be in my answer? Should be 9 total. What row of Pascal's triangle do I want to look at? The 8th. So you'll look at the row that's the same as the power. So I'm going to come back over here. This is my 8th row. Okay. And if you take a look at the 8th row, 1, 2, 3, 4, 5, 6, 7, 8, 9. See, it already has the 9 coefficients. Yes, sir. No, this is the 8th. Remember, you always start counting with 0 because anything to the 0 power is 1. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So the one we created was the 9th row. Uh-huh. No, you always start with 0. Always start counting with 0. Okay. So these are the coefficients I need. 1, 8, 28, 56, 70. So let me come back over here. So 1, 8, 28, 56, 70, and then it repeats those again. So 56, that's a 56. Then we're going to have 28, 8, and then 1. Now again, the coefficients of these terms are 1, right? So I'm going to see those numbers in my answer. If I have different coefficients, as we're going to start to see tomorrow, then I'm going to have to deal with those. I'm not going to see them. I'm going to use these to help me get what I need. Well, let's start with the very first one. I'm going to put a 1 right here. Now start the combination just like I was showing you a moment ago. I'm going to begin A to what power? A to the 8th. You always start with the power you're given, and then B to the 0. Plus, now I'm going to go to the second coefficient, 8, and I'm going to use the next combination. And I'm just going to create my answer as I go. So what would come after A to the 8th, B to the 0? A to the 7th, B to the 1st. Plus, move on to the next number, 28. What's the next combination? A to the sixth, b squared. And take a look at what we're doing so far. Remember, the a powers are decreasing, the b powers are increasing, and the sum is always 8. 8 plus 0, 7 plus 1, 6 plus 2. Is everybody okay with how I'm generating this? Any questions? Okay. So, Erica, what's the next term? Plus what? 56. B to the what? Third. That is exactly right. Perfect. Let's see here. Verunda, keep it going. What's next? Okay. Plus, Xavier? So see, remember, we're going in order of those coefficients. So now we're at 56 again. Perfect. There we go. And now let's see, Miriam, what's the next term? A to the third? A to the second, B to the sixth. Perfect. Alyssa, can you tell me the next term? 8. I'm sorry. A to the first, B to the what? Well, not fifth. Seventh. There we go. And then now plus our very last term, 1. Now A has a power of 0. B should be to the 8th. There's my answer. So if I were to take time to multiply it out, that is ultimately what I should get. So just kind of think about that. How much faster was that compared to actually performing the operation? It's much, much faster. And how many terms did I end up with? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. How we doing? Now this is Pascal's triangle. Everybody's okay? That's one method. So far, people really like Pascal's triangle. Not a whole lot of problems with it. Now let me introduce you to another method, combination. Yes, sir?
The amount of terms you get always more
Then the power? Yes, every single time. Every single time. So does anybody have any experience with combinations, permutations, things of that nature? Have you heard of those before? Most likely you've used them in determining probability problems. But here, combination, this C with the subscripts N and R, this is actually very useful in helping us to find coefficients of different terms. Okay, so what does the exclamation point mean? That means factorial. Okay, so here's the mathematical definition. It says n factorial is equal to n times n minus 1 times n minus 2 times, and that pattern is going to continue all the way to 1. So what you want to do is whatever value you're given, you want to multiply all the decreasing integers or whole numbers below that. Okay, and there's also one other idea. 0 factorial is always going to be 1. So let me give you an example. If I were to say 4 factorial. What this is actually telling me to do is start with 4, but then multiply by every decreasing whole number I have below it. So times 3, times 2, times 1. So 4 factorial would be what? 24. Okay, and these can get very large very quickly. Like if I wanted you to simplify 10 factorial, then that means 10 times 9, times 8, times 7, times 6, times 5, times 4, times 3, times 2, times 1. Okay. So does anybody have questions on a factorial? Hey. I believe there is. So Scholar, you're telling me you don't want to type in times? That's exactly what he's saying. Let me see here. If you go to A. No, I think it's, where is it? Didn't see it. Oh, okay. Right. Oh, there you go. Yeah, right over there. Okay. So yeah, it's on the right side. It's above that little flag below the enter button. Okay. There you go. Yes. Okay. So we're all good with the factorials. Okay. Well, let's take a look at what we call a combination. Now, really, I'm going to do just an introduction today. It's tomorrow when we're actually going to see a problem for the first time where we find a coefficient, we expand it. Okay, so here it is. When you're talking about the notation for a combination, the first subscript is always in. Okay, that's the power that you're raising your binomial to. That's going to remain consistent. The second subscript, that's what we call r. Now, what you're going to notice is that is the second term's power. Okay. So that first subscript is always in. It's the power you're raising on the binomial initially. The second subscript that we call r, that's always going to be the second term's power. Okay, so let me give you an example of the formula before I actually look at the pattern. What you do is take n factorial divided by n minus r factorial times r factorial. Now, you'll also be able to see it, for those of you moving on into calculus, you might see it, instead of written as a combination, you'll see it written like this. It's going to look like a 2-by-1 matrix, but it's going to have parentheses instead of the brackets. Okay, so let me give you an example. What if I wanted you to simplify the combination of 7 and 4? Now remember, the formula says n factorial over n minus r factorial times r factorial. Okay, the first subscript is always n. The second one is your r. Okay, so I'm just going to plug into this formula. So this would be 7 factorial over 7 minus 4 factorial, and then 4 factorial. Well, what's 7 minus 4? 3. So I'm going to go ahead and simplify this. 7 factorial over 3 factorial, 4 factorial, right? Now, the one thing you could always do is go ahead and figure out, yes, that's exactly what I was going to bring up. Instead of like figuring out 7 times 6 times 5 times 4 times 3 times 2 times 1, doing the same thing for the others and then simplifying, I might stop at a particular section if you don't have a calculator and go ahead and simplify. Let me show you what I mean. Instead of taking 7 all the way to 1, I would say 7 times 6 times 5, but I'm going to stop right there. Okay. Because 4 factorial would still have the 4 times 3 times 2 times 1, right? And below I have 3 factorial, 4 factorial. Well, just like Satish was saying, anything divided by itself is going to cancel, even a factorial. So see, it's going to drastically remove a lot of terms that I would have to multiply. Okay. Now, of course, this is if you don't have a calculator. If you have a calculator, boop, you push the button and that's it. But, you know, we want more of a challenge than that, right? Of course we do. Of course we do. So help me out. What is 5 times 6 times 7? Well, 5 times 6 is what? 30 times 7? 210. Divided by, now 3 factorial is 3 times 2 times 1. Okay. And you could also do that. You could simplify the 3 and the 6, but, you know, let's have some fun with the math. I mean, come on. You're still going to get the same answer. Right? Okay. But there you go. See, that's how the formula simplifies. Yes, Stephanie?
So would you cancel, like, or does it cancel?
No, just the 4. See, I still would have to deal with this 3. Now, if I wanted to, I could put times 3 factorial and cancel those out. It just depends on what you want to do. I would personally always simplify or cross out the largest factorial. Okay. Now, remember, this right here, the combination of 7 and 4, this can also be written as 7 and 4. And I know that Mr. Heinrich, for instance, prefers that particular notation to this one, but I like the combination notation. It's just basically preference. Okay. So there's the formula. Now, one other thing I want to go ahead and show you, we already took a plus b cubed and we expanded it, right? So we already know the answer we should be getting. But take a look. You'll notice the pattern here. You see how it goes a cubed, b0, a squared, b, a, b squared. You'll notice that variable combination. Isn't that the same as what we've been doing? But look at the combination. You'll notice here's the combination 3 and 0. Here's the combination 3 and 1. Combination 3 and 2. Combination 3 and 3. What is not changing? The thing on the top. The numerator. So what variable is that? N. That first subscript N is always the same in every one of those combinations. But when you start writing out the pattern here, you'll notice R starts at 0 and then it begins to do what? R increases. See, it went 0, 1, 2, 3. There's also one other thing I want you to notice here. You can always tell the value of R very quickly. R is the second term's power. When R is 0, we had b to the 0. R is 1, b to the first. R is 2, b squared. R is 3, b cubed. That's going to be very, very useful to you because if you already know the value, the power of the second term, should you immediately know the power of the first term? Yeah, because their sum has to be whatever you originally started the problem with. Okay. So this one is probably a little more hazy, and that's okay because we haven't had time to go through it yet. But we're at the end of class. The bell's about to ring. We'll go ahead and stop there. We'll do some more examples when we come in tomorrow. Okay. Good. Okay. Now remember, the current homework assignment you have over series, that's due when? That's due Friday. Okay. So tomorrow, we're just going to go ahead and take our time. We'll continue this. All right. Thank you guys so much. You have a great day. I'll see you later.